Hello everyone. I hope you are doing very well. So, let's start today's topic. As you all know, we are going to cover the JEE PYQs that has been there in the previous JEE examinations. So, let's begin our topic, that is NCERT chapter 3 Chemical Kinetics JEE PYQs part 2. Let's start. So, this is disclaimer. Let's begin with our first question. This is a JEE PYQ and this is covering the NCERT section 3.3.3 from our chapter Chemical Kinetics. The question is ratio of 14C to 12C in a piece of wood is 1/8 part that of atmosphere. If half-life of 14C is 5,730 years, the age of wood sample is how much of years? So, what is question asking? We have given the ratio of 14C to 12C. This 14 and 12 are representing the masses of the carbon. C is representing carbon. So, they are isobars, okay, having the same atomic mass. They are isotopes having the same atomic number and different masses, 14C and 12C. Okay, so masses are different, but atomic number are same. Atomic number of carbon is 6. So these two isotopes ratio in a piece of wood is 1/8 part of that of atmosphere. That means this ratio, whatever the value of this ratio is in the atmosphere, this ratio value has 1/8 of that value in the wood. This is what question is telling us. Now, if half-life of 14C, that is 14 atomic mass carbon atom, the half-life of this is 5,730 given in the years. You have to tell the age of wood sample in years. This question has been in the 2024 JEE examinations. So the options provided are 12,880, 17,190, 10,753 or 17,100. So you have given some time. So if I provide you a hint, basically you can solve this question using the half-life formula for the radioactive elements, okay, which we have been covered in the chemical kinetics chapter. So you have given some time, try to solve this and then you will see the correct answer. Okay, let's see. So for this given question, it is given that the answer for this question is 17,190. Okay, so this is the answer for this question. That means this is the age of the 14C in the wood sample in years. So what are the given quantities? First of all, we will see that we have given the ratio of 14C to 12C in the wood relative to the atmosphere, which is equals to 1/8. So this ratio has a value of 1/8 in the wood sample relative to the atmosphere. Okay, this is what we have given. Another thing we have given is, okay, so if you derive this, you can write this term which is given that the 14C to the 12C ratio in a piece of wood is 1/8 part of the present in the atmosphere, right? So this you can write it as that this ratio in the wood divided by this ratio in the atmosphere is equals to 1/8. This is what we have given. Okay, that means this 14C by 12C ratio in the wood relative to atmosphere is equals to 1/8. Another thing we have given is half-life. Half-life of the 14C is given as 5730 years. So the step 1, let's start to solve this. So step 1 includes that recall the radioactive decay law and its relation to the carbon dating. So remind that what was the radioactive decay and which kinetics or which chemical kinetics, reaction kinetics we are going to follow in the radioactive decay process. Okay, so you have to remember the radioactive decay law and the relation of it to carbon dating, because we are talking about carbon in this question. So general formula for the radioactive decay is given by Nt is equals to N naught e to the power minus lambda t. Okay, this representation is a general formula for the radioactive decay. If something is decaying radioactively, this is general representation for that. Nt is basically the remaining thing or remaining concentration at time t. N naught is the representation for the initial concentration for that radioactive element. E is exponential term, minus lambda t is a constant, and where t is given in the times. So okay, here also it is given that Nt is the number of radioactive atoms remaining at time t. So at time t, whatever we have the concentration or the number of atoms remaining after the radioactive decay process, that is represented by Nt. N naught is initial number of the radioactive atoms we have at time t equals to 0. Lambda is a decay constant and t is elapsed time. Okay, that is age of sample. How much is the age of sample, how much time it is taking in that decaying process, that is represented by t. So in the context of the carbon dating, this Nt and N naught are often represented by the ratio of 14C to the stable 12C, because 12C remains constant. Okay, now if you know that between that 14C and 12C, as they both are isotopes, the stable one is the 12C. Right, because we have studied that carbon has atomic number 6, carbon has atomic mass 12, remember? So 14C is relatively less stable compared to the 12C. Okay, so Nt and N naught are often represented by this ratio of 14C to stable 12C. Okay, because 12C is going to remain constant, so we can write it as that Nt by N naught ratio is equals to this ratio of 14C to 12C in the wood to the atmosphere. Okay, so we use the carbon dating process, or carbon dating or radioactive decay process, or the concept here, and we find the general formula for it. Every variable here in this equation is defining a thing or a term like Nt, N naught, lambda and T. Okay, now we are saying that in the context of the carbon dating, the Nt and N naught are represented by the 14C to the ratio of 14C to the stable 12C. Okay, C is carbon. So we can write it as that Nt by N naught ratio is equals to the 14C to 12C ratio in the wood to the atmosphere. Okay. Now, if you take the natural logarithm, that is ln, on both the sides of the decay equation, which was Nt equals to N naught e to the power minus lambda t. This is decay equation. If you take the log at both sides, because our equation is in the e form, exponential form, it will be easier if you take the log and then solve this. Okay. So when you take log, it will be ln nt by n naught. This n naught will go here in the denominator, and when you take ln, it will be ln nt by n naught is equals to ln of e to the power minus lambda t, and ln base e will become 1. So here only minus lambda t will come. Okay, because whatever go in the power, that will going to come in the product form in the ln logarithmic formulas. If you know that ln e to the power x will be equals to x. Okay, so using that formula, we are writing here ln nt by n naught equals to minus of lambda t, where we can also write it as this minus, this negative you can take here at the left hand side, and if you take this negative at this here in the left hand side, this negative will come here, right? Now, as I said, that whatever is present in the power, that will go in the product. So if we can follow the reverse rule also, that if something is in the product with the ln, it can go into the power, right? So that minus will go into the power of nt by n naught, and when you write nt by n naught to the power minus 1, you can also write it as n naught by nt, right? So nt by n naught power minus 1 will be n naught by nt. So this equation will become ln n naught by nt equals to lambda t, and n naught is the initial number of atoms we have for the decay element. Nt is the number of atoms remaining after the decay process at time t. T is time, lambda is decay constant. Now we substituting the carbon ratios. So lambda t equals to ln 14C by 12C in the atmosphere divided by 14C by 12C in the wood, right? Because nt by n naught we have written as equals to this ratio, and using the carbon dating context, because we are considering the nt and n naught as the ratio of C14 to the 12C, the stable carbon, right? So by using that, nt by n naught was the wood to the atmosphere ratio. So n naught by nt will become atmosphere to the wood ratio. So lambda t is equals to ln of 14C by 12C ratio in the atmosphere to the 14C by 12C ratio in the wood. Now we will do the step 2, which is substitute the given ratio into the equation. So we get the ratio, that is 14C by 12C in the wood divided by 14C in the 14C by 12C in the atmosphere, was given as 1 by 8 in our question, right? It is already it is this equation is already mentioned in our question. So we invert the ratio to put into our formula. So when you invert it, it will become atmosphere to the wood ratio, and here at the right hand side it will become 8 by 1. So this atmosphere by wood ratio will become equals to 8 by 1, which is equals to 8. 8 by 1 means 8. Now substitute this value of this ratio, which is coming out as 8, into the equation which is coming out from the step 1, which was lambda t is equals to this ratio, right? So lambda t is equals to this ratio, that means lambda t is equals to 8, because the value of this ratio we just find out as 8. So next we will do the step 3, which is the relating of decay constant lambda to the half-life t half, because remember we have to find out the age of the wood sample in the years. So the decay constant, that is lambda, is related to half-life given by the formula lambda is equals to ln2 by t half, right? So basically we are studying the radioactive decay process, so we are following the first order kinetics, in which the decay constant or rate constant is given as ln2 by t half. T half is representing the half-life. Now substitute, step 4 includes substitute the expression for lambda into the equation and solve for the t time. Okay, so this lambda we have identify as ln2 by t half. We substitute this into the equation and then we solve for the time which we have to find out. So when you substitute this lambda equals to ln2 by t half into lambda t is equals to ln8 equation, we will get ln2 by t half, that is lambda, multiply by t is equals to ln of 8, right? Now ln8 can be written as ln2 to the power 3, right? So we are wherever there is ln or log of something, try to simplify that. Okay, try to decrease that number as much as possible. Okay, like 8 you can reduce it to the 2, that like 8 you can write it as 2 to the power 3, and now you can apply the formula that ln m to the power n will be n ln m, right? Something is in the power that will go in the product, so it will become 3 ln2. ln8 you can write it as ln2 to the power 3, which can write it as 3 ln2. So our equation will become ln2 by t half, this is the value of lambda, multiply by t, that is time, is equals to ln8. ln8 is 3 ln2. Okay, now here ln2 is present in both the sides, so it will cancel out, and from here easily you will get the t expression. So t that is 1 by t half times t is equals to 3. So t will become equals to 3 multiplied by t half. Now we will solve for the t, because that is what we have to find out, the age of the wood sample. So time will be 3 multiplied by the half-life. Half-life we have mentioned, remember, 5730 years in the question. So plug in the given half-life value. So we have given t half equals to 5730 years. So t will become 3 multiplied by 5730 years according to this equation, and when you solve this product, t will coming out as 17,190 years. Okay, and that's how this much is the amount, or this much is the age of our wood sample going to be in the years, and that is our correct answer. Okay, so I want to mention one thing. If you are having any doubt in between the session or on any slide, you can ask in the chat box. Okay, so let's move to our next question. So this is a JEE PYQ covering the NCERT section 3.3. The question is, R is equals to K times A. R is representing the rate, K is representing the rate constant, A is representing the concentration of the A. For a reaction, 50% of A is decomposed in 120 minutes. So we have given that the A, which is our reactant, is decomposing 50% in 120 minutes. Time taken for 90% decomposition of A is in minutes. So you have to tell the time in the minutes the A will take in its 90% decomposition. This question has been in the 2024 JEE examinations. The options provided are 275.48, 382.93, 398.8, or 289.59. So you have given some time, try to solve this, and then we will see the correct answer. Okay, let's see. So for this given question, the correct answer is given as 398.8. So what are the given values we have? First of all, we will see that what are the given values. as you can see, we have given the rate equation, the decomposition time, that when 50% of A is decomposing, it is taking 120 minutes. So the given thing is rate law, which is given as R equals to K times A, and this implies it's a first order reaction. Half-life is already given, which is 120 minutes. Half-life, why? Because 50% of A is decomposed. 50% means the half of the concentration of A is decomposing in this much of time. That means that time is going to be its half-life. Reaction is 90% complete. When we are asking the time, the reaction is finally 90% complete. That is also what we have given in the question. So the step 1, when we try to solve this, the step 1 includes that the confirming the order of the reaction. So if you see that given rate law is R equals to K times A concentration. This is the rate law given in the question. So in this expression, the concentration term, that is the A, is raised to the power of 1. Okay. So A concentration is having the power of 1. And if you remember, we identify the order of the reaction by looking at its rate law and seeing that what is the power that is going to present on the reactant's concentration. Here only A is a reactant and in its power only 1 is present. That means this is telling us that it's going to be a first order reaction. So therefore the order of the reaction is 1. Now, the step 2 include relate half-life to the rate constant K. Okay, so when you relate the half-life, that is T half, to the rate constant K, how can you do it? In the first order kinetics. So we apply a formula for a first order reaction. Half-life is related to the rate constant by the following formula. K is equals to 0.693 by T half. Or you can also write it as K equals to ln2 by T half. Okay, T half is half-life and K is a rate constant. Now we know that half-life is already given for A, that is 120 minutes, right? So we put this T half is equals to 120 minutes in the above equation to get K equals to 0.693 upon 120 minutes, right? And when you're going to solve this, we will include the step 3rd, that is use the integrated rate law for the first order reaction. Okay, now we apply integrated rate law for first order reaction. In the first order kinetics, we have studied the integrated rate law in which the K, that is rate constant, is relating with the T, that is time, and ln term is also coming, right? And the concentration at different time, initial and final, is also coming. So we apply that integrating rate law for first order reaction. The integrated rate law for a first order reaction is K rate constant is equals to 2.303 by time log of A naught by AT. A naught is representing the concentration present at T equals to 0, time equals to 0 initial, and AT is representing the concentration at some time. So A naught is initial concentration of A, AT is the concentration of the reactant A at time T, T is time, K is rate constant. 2.303 here is the conversion factor from natural logarithm ln to common logarithm, that is log 10. Okay. Step 4 include determine the ratio, that is A naught by AT for 90% completion. 90% completion means the 90% of reaction has already been done, right? 10% remains. So you have to determine this ratio to apply in the integrated rate law for a first order reaction. So for the 90% completion, you have to determine the ratio A naught by AT. So if reaction is 90% complete and it is given, it means that 90% of the initial reactant has been consumed, right? So 90% completion means our reaction 90% is complete, and also the initial reactant 90% has already been consumed. Now let's assume that the initial concentration A naught is 100 in the arbitrary units, for example 100%. Wherever percentage is given, we try to consider the initial thing as 100%. Like something is 100%, then it is changing by 50% or 90% in this case. If 90% is consumed, then the amount that is reacted is 90, right? Because initial reactant, 90% of initial reactant is consumed. That means the amount that is reacted with each other or with the molecules to get the product, to become the product, that amount is going to be X, which is equals to 90. Amount that are remaining at time t, that means AT, that will be A naught minus X. Okay, so A at T, that means the concentration of A reactant at time T equals to the A naught, the initial concentration, minus X, the amount that has been reacted. So it will be 100 minus 90, that is 10. So 10 is the amount of the reactant that is going to be left after the 90% consumption of the reaction. Now the ratio A naught by AT is equals to 100 by 10, because A naught we considered as 100 or 100%. AT is coming out as 10 or 10%. So 100 by 10 will become 10. So this ratio will become 10. So this is the step 4, and we are going to determine this ratio, and we determined it. We calculate it as equals to 10. Now we do the step 5, which is substitute all the non-values in the integrated rate law and solve for T, right? Because we have to identify the time that is going to take by the reaction for 90% decomposition of A. So time is only given in the integrated rate law equation. From there, we substitute every value which is already known to us or which we have just simplified, and then we will get the value for T. So from the step 2, we have K, that is rate constant, as 0.693 by half-life T half. From step 4, we have the A naught by AT ratio equals to 10. Substitute these into the integrated rate law, which is already given in the step 3. So the integrated rate law was K equals to 2.303 by T log of A naught by AT, right? So we know the K is 0.693 by T half. It is equals to 2.303 by T. T is what we have to find out. Log of A naught by AT will become log of 10, because A naught by AT is 10. Now log 10 will become 1, because log 10 is 1, because base and number both are same. So the equation will simplifies to 0.693 by T half equals to 2.303 by T, since log 10 equals to 1. Now we rearrange the equation to solve for T, because T is the only variable present. So T will be equals to 2.303 multiplied by the T half-life divided by 0.693. Other things have cancelled out or maybe going to be equals to 1. So substitute the value of T half. We have already T half also, but that is 120 minutes already given in the question. So we put this here in this T value, and T will be 2.303 multiplied by 120 minute divided by 0.693. So T will be, perform the calculation. We calculate this fraction in the step 6 and get T equals to 276.36 divided by 0.693. So T is coming out approximately equals to 398.787 minutes, or the time required for the reaction to complete 90%, which is what our question was asking. The time is going to be equals to 398.8 minutes approx. Okay, hence this will be going to be our correct answer for this question. So what we did in this question, we simply use the given half-life. First of all, you should have to know that the given quantity is half-life, nothing but half-life for the reactant A. You should have to know the order of the reaction to apply the correct formulas for the order and the rate constant and the half-life. So you have to calculate the time taken for 90% decomposition of A. If you have determine the order of the reaction, then you can apply the rate constant and the time relationship equation to get the time taken for the reaction for 90% decomposition of the reactant. Okay, and from that you can calculate the time, and here in this case it is coming out as 398.8 minutes. Okay, let's move to our next question. So this is a JEE PYQ and this is covering the NCERT section 3.3.2. The question is asking, following data were obtained during the first order thermal decomposition of a gas A at constant volume. Okay. So we have given the tabular data. If you can observe, this data obtained from this data obtained during first order thermal decomposition of a gas A at constant volume. So this reaction is A, that is in the gaseous form, is undergoing the decomposition process and giving us 2B plus C. Both are in the gaseous phases. The tabular data showing the first order thermal decomposition of a gas A according to this reaction. If you see, we have given 3 columns: serial number, time in the seconds, and total pressure in the atmosphere. So time at time t equals to 0. The total pressure was 0.1 atmosphere. At time 115 seconds, the total pressure will become 0.28 atmosphere. So the rate constant of the reaction is dash multiplied by 10 to the power minus 2 second inverse. So you have to calculate the rate constant of this reaction, that is K. And you have to answer your answer in the nearest integer. So this question has been in the 2024 JEE examinations. The options that are provided are 2, 6, 3 or 14. So you got some time, try to solve this and then we will see the correct answer. Okay, let's see. So for this given question, the correct answer is 2. The rate constant of the reaction is going to be 2 multiplied by 10 to the power minus 2. So what are the given things in this question? We have given the reaction according to which we have to follow the calculation of the rate constant. So reaction is A in the gaseous forms converting to 2B in the gaseous form plus C in the gaseous form. Initial pressure of A at time t equals to 0 seconds is given as 0.1. Total pressure at time t equals to 115 seconds is given as 0.28 atmosphere. Let's start to solve this. The step 1 includes set up the pressure changes based on the stoichiometry. Okay, so based on this reaction already given, set up the pressure change, that how with the time the pressure is going to change. So let's say P naught is representing the initial pressure of our reactant A. Let's say X is the decrease in the pressure of A at time t. Okay, some amount of decrease in the pressure is happening in the presence of the A reactant at time t. So reaction is A converting to 2B plus C, right? initially at time t equals to 0, the A pressure will going to be equals to P naught. 2B having 0 and C is having 0 pressure at the initial time. But at the final time, at time t equals to T, okay, the A pressure has become P naught minus X, some amount of decrease in the pressure of A. The 2B will be 2X and the C will be X. Okay, this is the stoichiometry. Now at time t equals to 115 seconds, because only two are given, 0 and 115. So at t equals to 115 seconds, the partial pressure of A, that is PA, is going to be equals to 0.1 minus X, because P naught is 0.1. Right? P naught means at time t equals to 0, what is the total pressure given? So total pressure given at time t equals to 0 is 0.1. We apply here the partial pressure formula for the A, that is the reactant. So PA is given as 0.1 minus X, that is P naught minus the delta P, okay, which is going to be X, because X representing the decrease in the pressure of the A. Partial pressure of B, let's say PB, is equals to twice of X. You can see here in this reaction also that at time t, the A pressure will become P naught minus X. That means 0.1 minus X. And the 2B partial pressure or B partial pressure will become equals to 2 of X. Similarly, the partial pressure of C product, that is PC, is going to be equal to X. Now we do the step 2, that is use the total pressure to find the value of X. Now this X is a variable, right? We don't know its value, the change in the pressure, the decrease in the pressure. So we use total pressure to find the change in the pressure X. The total pressure at the time T, that is P of total, is sum of partial pressure of all the gases present in our solution or present in our container. Right? So you have to sum the partial pressure of all gases to get the total pressure at time t. So total pressure is equals to PA plus PB plus PC. PA is representing the partial pressure of A, PB is representing partial pressure of B, and PC is representing partial pressure of C. Their sum is equals to total P, and you put the formula. PA is 0.1 minus X, PB is 2X, PC is X. When you solve this, the P total is coming out as 0.1 plus 2X, because this minus X plus X cancel out, plus 2X will remain. We have given that the total pressure at some time, let's say 115 seconds given. So at t 115 seconds, the total pressure is given as 0.28. So you can write this total pressure equation as 0.28 equals to 0.1 plus 2x. Now the only variable remain in this equation is x. So we now going to solve for the x. So 2x is equals to 0.28 minus 0.1, that is equals to 2x equals to 0.18. Okay, so basically we are solving it for the x. So 2x is coming out these two differences. 2x is equals to 0.18. X from here going to equals to 0.18 divided by 2. That means x is equals to 0.09. Now we do the step 3. We follow the step 3, which is saying calculate partial pressure of A, which is remaining at the time t. That means PT now you have to find out. So partial pressure of A at any time t is given by PT equals to P naught minus X. Right? X where is representing the decrease in the pressure. So PT, that is total pressure, will become P naught. P naught is 0.1 minus the X. X is 0.09. When you solve this, the total pressure will be 0.01. Now we do the step 4, which is use the integrated rate law for first order reaction to find the K. Okay, if you remember, we have already mentioned in the question that this question is following the first order thermal decomposition. So that's why we are using here integrated rate law for first order reaction to find the K, that is rate constant. So formula is K is equals to 1 by T ln P naught by Pt, right? K we know, T we know, P naught and Pt, they are the one that we also know, right? Okay, so K, that is what we have to calculate, the rate constant. K is representing rate constant. So substitute the known values. T we know, that is 115 seconds. P naught we know 0.1 and P total is coming out as 0.01. That is going to be very less. Okay. So these are the given values we have already given. You can directly substitute these values in this formula of integrated rate law for first order reaction. So K will become equals to 1 upon the time. Time is 115 seconds. Ln P naught is 0.1 divided by the PT. PT is 0.01. Now you have to solve this. So K, that is rate constant, is coming out as 1 upon 115 seconds multiplied by ln 10. The step 5 we are going to follow is the calculation of the value of K. So K, ln 10 is given in the value of the K. Ln 10 you can take it approximately equals to 2.303. Okay, and then you can use that in this equation we derived. So K is equals to 1 upon 115 multiplied by 2.303. Okay, so K equals to 1 upon 115 multiplied by 2.303. You can here directly or simply multiply the two terms and get the value of rate constant. So K is coming out approximately equals to 0.020026 second inverse, or this can also be written in scientific notation as rate constant K is equals to 2 multiplied by 10 to the power minus 2 second inverse. Okay, and this is going to be our correct answer. Okay, so which PT you are talking about? PT means platinum or what? Okay, so this is the question we just derive the value of the rate constant, that is 2 times 10 to the power minus 2, right? Okay, the pressure is given in this table. No, at time t equals to 0 we have given total pressure 0.1, that is P naught. At time t equals to 115, that is P total is given as 0.28, right? So we use this value of pressures P naught and PT in the integrated rate law equation for the first order reaction. Okay, and then we will put that and the known values to find the rate constant value. Okay, so let's move to our next question. This is a JEE PYQ and this is covering the NCERT section 3.3. Question is, consider the following data for the given reaction. We have given the reaction 2HI giving us H2 plus I2 in the gaseous form. We have also given the table in which we have performing some experiments, given the concentration of the HI, that is reactant, and the rate for the reaction. So in the first experiment, HI concentration is 0.005. The rate for the reaction is 7.5 times 10 to the power minus 4. In second experiment, HI concentration is 0.01 and rate is 3 times 10 to the power minus 3. In the third experiment, we have HI concentration as 0.02 and the rate as 1.2 times 10 to the power minus 2. You have to tell the order of the reaction. Okay, so this is the question that has been there in the 2024 JEE examinations. The options provided are 1, 2, 3 or 0. So you have to find out the order of the reaction, remember, okay, following the given tabular data we have. You have given some time, try to solve this, then we will see the correct answer. Okay, let's see. So for this given question, the correct answer is option B, that is 2. Let's see how. So we have to determine the reaction order from the initial rates we have given for 3 experiments. So to find the order of a reaction, which is represents by N, with respect to a reactant, for example HI here in this case, from experimental initial rate data, follow these steps. So if you are following these steps, you can identify the order of the reaction with respect to reactant. Steps involved are, the first one is choose 2 experiments. So we have given 3 experiments, you have to choose the 2 experiments. Select 2 experiments where only concentration of reactant, that is HI concentration in the question changes. Like if you see in these 2 experiments, the reactant concentration is changing, right? So select any 2 experiment where the concentration of reactant in the question is changing and all other reactant concentration is remaining constant, right? We use the experiment 1 where the initial concentration of HI is given as 0.005. Initial rate for this concentration is given as 7.5 times 10 to the power minus 4. We use experiment 2 where initial concentration is given as 0.01 for HI represented by HI2, and the initial rate for this is given as R2 equals to 3 times 10 to the power minus 3. Now we follow the second step, that is set up the ratio of rates. We know the rates, right? We use rate law, which is given by rate equals to rate constant multiplied by the concentration of the reactant to the power something. Okay, that something is nothing but order, which is representing the reaction order, representing by N. Okay, so we use the rate law because as you know that in the question we have given the reactant concentrations and the rate of the reaction, right? This both quantity, the reactant concentration and the rate, is mentioned in the rate law. So we use rate law, which is given as rate equals to K times HI concentration to the power N. N is representing order of reaction. Divide the rate law for higher concentration experiment by lower concentration one, and this will going to eliminate the rate constant K. Okay, so what we are going to do, because we are talking about the same reaction but only we are changing the concentration and due to which the rate is going to change. Other than that, rate constant is the constant. Okay, so we are going to divide the rate law first of all for higher concentration by lower concentration. Okay, so we take this lower concentration and this higher concentration and we divide them. This step is going to eliminate the rate constant, that is K present in the rate law. So rate 2 divided by rate 1. Rate 2, why? Because the concentration is higher in the second experiment. So rate 2 by rate 1 equals to HI2 by HI1 to the power N. Now we follow the step 3, that is substitute the values and simplify. Because we have the values, so plug in the given experimental values into the ratio and then we divide it. So we know the rate values for 0.01 higher concentration. We know the rate is 3 times 10 to the power minus 3. For lower concentration, the rate is 7.5 times 10 to the power minus 4. Similarly, this is equals to 0.01 higher concentration divided by lower concentration 0.005 to the power n. Okay. Now, if you see here, k is already eliminated. The n is only the thing that is going to be remain, like variable, from which you can identify the order. So left side, which is given as rate, if you solve it separately, so 0.003, 3 times 10 to the power minus 3 is 0.003, divided by 7.5 times 10 to the power minus 4 is 0.00075. I hope you know these, decimal representation, decimal replacement to convert into conversion of this number from 10 to the power to something like this in the decimal form. Okay, so something like 3 multiplied 10 to the power minus 3 means 3 has here as 3.0, 3 decimal 0. You can write 3 as 3 decimal 0, right? So minus 3 in the power in the 10 means this decimal will go in the left hand side 3 times. Okay, and that's how you will get 0.003. So if you solve this fraction for rates, it is going to be equals to 4. Right side, which is given as concentration ratio, if you solve this separately, so 0.01 divided by 0.005 is going to be equal to 2. So we have solved the left side and the right hand side. Only the thing that you have to calculate is n. So this simplifies the equation to 4 equals to 2 to the power n, right? So we put this left hand side, that is 4, is equals to right hand side, that is 2 to the power n. Okay, now 4 you can write it as 2 to the power 2. Okay, 2 to the power 2, because 2 times 2 is 4. So 2 to the power 2 is equals to 2 to the power n, and from there you can calculate n. So step 4 involves the solving for the order, that is n value. So since we know that 2 square, that is 2 to the power 2, is going to be equal to 4, n is going to be equals to 2, right? That's how this left hand side and the right hand side is going to be balanced. So the order of the reaction with respect to the HI, that is the reactant HI, is 2. Okay, I hope you understand this. As I said that 4 is coming out as equals to 2 to the power n. 4 you can write it as 2 to the power 2. So 2 to the power 2 equals to 2 to the power n. From there n will come out as 2. Okay, that means the order of the reaction, this given reaction, is 2. Okay, and 2 will going to be the correct answer. Okay, so that's all for today's chemistry session. Thank you so much for joining this.